Hello everyone, welcome back to Imaginary Hub. In this lecture, we are going to implement a concept called as principal component analysis. In previous lectures, we have studied most of the concepts of linear algebra. We have seen elimination methods, inverses, symmetric matrices, rectangular matrices, transformations, and we have seen a concept called as eigenvectors and eigenvalues, right? And from that, we have connected that topic to a machine learning method called as PCA, Principal Component Analysis. And in last lecture, on Wednesday's lecture, I believe we have studied how do we visualize PCA, what is the intuition of it. Now, in this class, what we will do is that we will try to understand how can we implement the principal component analysis concept in terms of code, and we will take a data set and we'll put PCA on top of that, and we'll do a dimensionality reduction, and from the extracted answer we'll try to extract the patterns or and draw conclusions and all the things. So with that being said, enjoy the video. It's gonna be this build Sunday lecture is going to be a bit different. In our previous build Sundays, we directly build products. We have build racks and all. Now we are going to study algorithms, and we will see how we can implement those algorithms in terms of code. So enjoy it. And if you have any doubts, you can comment it down, and you can find the GitHub link in the description and in the comment section as well. And whatever the code we are showing, whatever the whiteboard information I have written, right? You can find all the notes, all the code in the GitHub repo. So with that being said, enjoy it, and I'll see you in the lecture. In the previous lecture, what we did is we have studied a concept, and before studying the concept, we have revised most of the concepts in linear algebra, right? We have seen different sort of topics, theoretical concepts, and within 15 to 20 minutes, I have given you a complete picture of the all the concepts that we have studied till now in linear algebra, right? And after that, we have studied a concept called as PCA, right? Before PCA, like in linear algebra, we have studied something called as eigenvectors and eigenvalues, right? In eigenvectors, I have given you a demonstration of what we did and how do we find eigenvectors and all the concepts of mathematical concepts of eigenvectors as well. If you go up a little bit, you can see before going to PCA, I have shown you all the mathematical stuff of how do we find eigenvalues and eigenvectors, and along with it I have shown you the intuition of how do we even actually imagine it, right? So after talking about eigenvectors and eigenvalues, we have gone through a implementation part of eigenvectors, which is PCA, right? Principal component analysis. I hope I'm taking it correctly, pronouncing the full form correctly, right? In principal component analysis, I have told you that why do we use it, and how do we find it manually, right? If I'm a person who I don't have, let's assume that I don't have computer, then in that case, how do I implement PCA, right? And how do I actually find the different dimensions like PCA1, PCA2 for the given data? I have talked about that, and we did a numerical as well. Now in today's lecture, this is going to be a bit different. What we will do is that I will quickly go through the concepts of how we find PCA manually, right? That is the first thing I'm going to show you, and then I will tell you that how are we going to program that. So let me quickly go and tell you that in PCA, right, what we did is okay, imagine like we have data points, right? Imagine we have data points and two-dimensional data points. So we plot the data points in this fashion, right? And the line which is closest, or you can say the line which has the least distance to the from the points, right? The line, what we do is generally if we are using manually, if we are finding the PCA values manually, then we take a line, we keep on rotating this line each and every degree until and unless the line has the minimum distance from the data points, right? And the line which has the minimum distance from the data point will become our PCA line 1, and this stores most of the information. And what we do is that we will draw a perpendicular line called as PCA2, right? And this will be our another, the line which is perpendicular to PCA1 will be a line called as PCA2. And what I said you is that this lines PCA1 and PCA2 are eigenvectors, are eigenvectors lines. So whatever the vectors which are staying in this line are eigenvectors. So in last lecture, it has been many days, right? So what we did is I have told you about eigenvectors. I have kept it aside and I have told you a concept called as PCA, right? I'll reiterate the statement of why do we use it and everything. But we studied PCA, and in telling the concepts, I have showed you that how do we actually use, or why do we use the concepts of eigenvectors in PCA. Okay, now let's assume that I don't want to go fast. I don't want to go like really, really fast. So what I'll do is that I'll tell you, I want you to have one understanding that you should know some parts of linear algebra, the parts which we have studied till now. You should know that, you should have understanding of that, and you should know what are eigenvalues and eigenvectors. If you are good, then I'll go with implementation of PCA. I'll go with talking about what is PCA and all. So, right, that is the quality, that is the nature of PCA. It won't give you unnecessary data. It always gives you a data which is valuable, which is like different, which has some sort of variance. I'll talk about that. But remember these two statements. These two statements are really, really important. Now, take example. Let's take example to understand where do we use it and how do we use it. So imagine that I'm in a classroom. I'm in a classroom. Um, in classroom, there are students, and each student is having, uh, let's say, a teacher is arranging students, right? He's allotting the seats to students, and this allotment of seats is happening based on heights, right? Just imagine a case. So what happens is that the student, let's say we have 10 students, let's say um, A, student B, student C, student D, right? I have taken 4 students, and student A height is 180 centimeters, 170 centimeters, 190 centimeters, and 110 centimeters, right? So here, if you take this data, we have students, and each student has one feature, and that feature is height. Okay, now the teacher is assigning seats to students based on their height, and the students who have least height will sit in first rows. The student who have uh, you can say more height, they'll sit in back rows, like backward rows, right? Back benches. Now how can we visualize this data? This is my question. So we can easily visualize that, just draw a number line, and this number line is student's number line, and what we do is that this number line is height number line. This number line represents height. Okay, now this is 0, right? Just imagine 180, 170, something like that. This is point A, point B, student A, student B. So what this points represent? This points represent each and every individual student. Okay, now this is one example. If we have a data, and for that data there is one feature associated with it. Here the data is about students, and the features, the qualities or you can say the dimensions is one dimension, only one feature. Now just imagine that we have students marks. I'm taking another example that let's say I have student data, and here I'm gonna store math marks, physics marks, and let's store two things for now. Let's say student A 90 marks and 80 marks, student B 30 marks and 10 marks, student C 40 marks and 50 marks, and student D 100 marks, 95 marks. Okay, now if you try to plot this data, then what we will do is that we draw our x plane and y plane, and x-axis will represent math, y-axis will represent physics. Okay, now we just plot the points, we just plot the features. Right here I have like 90 math, 30 here, 40 here, like this 50 here, something 90 here. Like I'll plot the points, whatever the features are there, right? I'll plot it here, right? And whatever the second features are there, I'll plot it in second axis, and the points I get, let's say this is 30 comma 10, right? So this is this point 30 comma 10 represents student B. Similarly, if you take another point, let's say 90 comma 80, right? This point represents student A. So the point I'm trying to make here is that when you combine features, right, that can be any feature. Like here we have on x-axis math, y-axis physics, and whatever the intersection point we are getting, that point is a student, right? It is, that point is representing a student. Now my question is, can we, by plotting this, by doing this, right, can we tell that if student is having good marks in math, then he's also having good marks in physics? So when you plot the graph, you will understand that the students who are having low marks in maths will eventually like having less marks in physics as well. So from this, what we are doing is that we are drawing the points, and from seeing the points we are visualizing the information. Okay, now imagine that I added another subject, I added chemistry. In chemistry also, what we do is that we draw another line, a three-dimensional line called as chemistry. Okay, got it, got it. Now what I want you to do is that I want you to imagine a new example. Let's say the example is student is in BTech, right? And in BTech, how many exams do we have? If you take 8 per semester, then he might have 80 subjects, right? 10 semesters or 8 semesters, 8 just 64. Let's say he will have 64 subjects. Now, let's say we have student A. Student A will have subject 1, subject 2, subject 3, like this. He will have 64 subjects. Similarly, student B will also have 64 subjects. Okay, so how many features are there? The number of features here are 64. It means they are 64 dimensions. Can we visualize 64 dimensions? Can we visualize a data which has 64 dimensions? Yes. Like for example, just assume that there's some way you have created some way, and from that method you're trying to see n dimensions. Then what you can do is that just plot the points, and automatically you can see from the pattern, you can see like which students are having, which groups of students are having good marks, and which group of students are having less marks, right? Once you can able to plot a 64 dimension like space, then you can easily tell. But my question is, can we do that, right? I don't think so. As humans, I don't think so we can visualize 64 dimensional space, or the data which is lying in the 64 dimensional space. So in that case, what we do is that we use something called as principal component analysis. So what this principal component analysis will tell us is that it will take n-dimensional data. It can be, for our example, it is 64 dimensional data. So we will take 64 dimensional data and we will try to take the useful information only. Okay, we'll take the useful information only and we will plot graphs, right? We'll plot lines, and this, whatever the lines we plot, right, this will show the same pattern. This will show the same pattern as compared to a 64 dimensional space. For example, let's say you have plotted this 64 dimensional graph. So the pattern you will get, right, this pattern and PCA will give you the same pattern. The difference is in normal methodology, we are drawing 64 dimensional space, and from that we are getting the data patterns. But here, within one or like 2-3 dimensions, within 1-2-3 lines, this 3 lines is telling you the same data, same information, which we are getting from here. So I hope you have understood why do we use it. Now, how do we use it? What is the thing? What are the procedure? What is the procedure of using it? I'll tell you now. This is the algorithm. I think you should make notes from here. So implementation of PCA is that the first and foremost thing is calculate center. So how do we calculate center? So let's take an example. Let's take a mini example, which we use to implement our algorithm, and we'll code that as well. So I'll take a simple example. Let's say I have student, student A, math mocks, student, math, and physics. I'm taking two-dimensional data because it is easy to understand for us. Okay, so I'll write, let's say CGPA 8, 9, and student B 9, 9. Just very simple example, and 5, 4. Okay, now what we do is that we take the center of this data. Now, how do we know the center? The simple answer is we know the formula, right? In geometry in 11th class we have studied, right? Let's say there are two dimensions. Center of x comma y would be all the points given, like x1 plus x2 plus x3 up to xn divided by n, comma y1 plus y2 plus y3 up to yn if they are n points divided by n. Okay, okay. Now here the point we should notice here is that we don't actually have to imagine 64 dimensional space. Like from formula we can easily calculate center. For example, let's say there are 64 dimensions, x comma y comma z comma alpha comma something something up to 64. Then you can directly put this formula and you can get the centers of c1, c2, c3, all the, for each and every single line. Like this is x line, this is y line, this is z line. For all the points you will get the centers, right? For each line x, y, z, alpha up to 64, you will get it, and this will be the center of a 64 dimensional space. So if you see the formula, you don't have to actually visualize it. Just put the values here, and no matter how many dimensions are there, you can easily get the center. So the first method is we calculate the center. Okay, now in our case we have math, right? So center of math comma physics would be all math points, so 8 plus 9 plus 5 divided by 3, comma all physics points, 9 plus 9 plus 4 divided by 3. So this will give us, I'm taking an example, practical example, for which we can easily understand, right? If I talk about just randomly with theoretical concepts, then you might not understand. Having example is a safe side. So if I add it here, how much will give me 14, 14 plus 8, this will give me 14, 14 plus 8 is 12, 22, 22 divided by 3. I hope I'm doing right calculations, but calculations doesn't matter here. 18 plus 4, again it will give me the same thing, I believe. Yep, 22 divided by 3. So this will be my center. Now after calculating center, the second step here is calculating variance. Now what is variance? This is a important concept. I'm writing the definition of variance here. In PCA, the meaning of variance is, or I'll just write here, in PCA, variance tells us how much the data has spreaded slash varies in that space. What do I mean by this? The definition of variance is that it tells you that how much, let's say I have a point, right? I'm drawing a example, right? Let's say this is my data and this is my data. I'm taking two examples. So in example one, the number of points is very little, and if you see the overall spread, this is the spread. It means that if you observe the cloud, which is the example one is forming, it's a very small cloud. The spread is very little. It means that it has less variance. Now, if you see this cloud is a very big cloud. In example two, the spread of the points is very large. It means it has high variance. Yep, understood definition of variance. Now, why do we need it? To understand like why there is a need of variance, you need to understand that what I have told you, PCA always gives you the needed, or you can say informative data only. And you tell me that uh, which data is useful? The data which has same points, let's say here in our example, all 64 students is having same marks. Is it a informative, like useful data, or the data which has different values? Which data is important? Which data set is important? And from which data sets can you extract patterns? For example, let's say your task is to make student sit in ascending order based on their heights. Okay, now like you tell me which type of data is important, right? Which is valuable. Let's say I have data A where every student is having the same height, or I have another sample in which student varies a lot. The height of student varies a lot. So if I give you the data set, then you tell me based on from the data I have given you, from which data you can extract a pattern. The answer is the data which has more variance, the data which has different sort of numbers, different types of numbers. The numbers should vary a lot. When the number varies, then you can tell, oh, this student should sit here. But if every other student is having the same height, then how can you tell? So variance is the most important parameter which tells you how much the data has spreaded in that particular dimension. And based on the spreadness only, based on the variance only, you can tell that which data is important and which is not. For example, in our problem statement, I'm going back. Let's say you have decided to make students sit based on their height, and if that feature, that height feature is same for all students, then you need to see some other thing, right? You need to take a feature which varies, because if the data is same, then there is a pattern, but that pattern is not useful. You cannot like draw uh, useful conclusions from that data. I hope you got the point, right? So this data 2 is far more useful, far more important than this data 1. Why? Because this data 1 has little spread. It is the same data, right? If the data, if like for example, if you draw, like just imagine that all students, like all 100 students are having same marks, then what it will give you, will give you a point, right? If all like students, if let's say all students, student A is having let's say 10 marks in physics, 10 marks in math, 10 10 10 10, then point A will be equals to point B is equals to point C. It's just the same point. And my question is, what can you conclude from a single point? You cannot. You need a cluster of points to draw any sort of patterns. So that is why we need the data which has more spread. And to get or to tell which data has more spread, which data does not have more spread, we use a parameter called as variance. Okay, so this is the definition of variance. And how do we calculate variance? Variance of math comma physics in our example, right? Before we go into this formula, you need to understand. Okay, I think I have forgot one step. Let me come back. Variance is the third step. Wait. Control Y. Let me just erase it. Okay. If you get any doubt, please do ask me, because these concepts are important concepts to understand. Okay. So before we go to variance, what we do is that we recenter the data. So if you remember, I have told you that let's say I have the data, whatever the data provided, and from this data points, I got a center as here, right? Now, if you see from origin, this point is having high value. This point is also having some high value. This point is having some high value. Now, if we try to do computations with high numbers, then it will require more energy. The math will be more complex. So what we will do is that we will recenter here. We will recenter the origin, and what we will do is that we will make the center as origin. To make center as origin, what we do is that we take the center point, we subtract it from every other point. And when you subtract the center with every other point, what happens is that your data will become something like this. So let me use blue pen only. Your data will become like this. So you will have your axis and the center will be here, and all points will remain the same. Okay, all points will remain the same, right? The structure will be remain like the structure overall spread here is this spread, and after restructuring as well, this is the spread, right? You will get the spread. The spread is same, right? Yeah, so we restructure, or you can say recenter the origin in order to reduce the number of mathematical operations. And you might ask, like, if we change the coordinates of coordinate like points here, let's say I have point 1 and the coordinate are 10 comma 20, right? So if the coordinates are 10 comma 20, then after recentering the point, the p point will have different numbers, right? The answer is yes, it will have different numbers, but But the point you should notice here is the cloud is changing? No, right? If the cloud is not changing, then the information, or you can say the pattern conclusions will not change. PCA is not about which point is having which location. It's about how's the cloud. What is the structure of the cloud? That is important. So what we do is that we recenter the origin and we uh, change all these points. So here we will subtract, our new points would be math, comma physics. So what we do is that we take all the points 8, comma 9, right? So 8 minus 22 divided by 3, 9 minus 22 divided by 3. Similarly, 9 minus 9, 9, right? So 9 minus 22 divided by 3, 9 minus 22 divided by 3. And 5 minus 22 divided by 3, 4 minus 22 divided by 3. So these are the new points of the given data. This points has the same spread, has the same shape. The cloud shape will be the same. The only thing is we have recentered. We have taken this data, recentered it to origin. Now the center is 0, comma 0. So if you try to calculate the center of this points, you will get 0, comma 0 as output. Okay, so we have restructured the origin, like relocated the origin in good words. Okay, now the third thing is variance. So to calculate variance, what we do is that we take the squares of these points. So variance of math comma physics is equals to, we take all the points, right? This is known as deviation of A. So deviation of A is equals to this, deviation of B is equals to this, deviation of C is equals to this. So we take the squares of each deviation point, sum them. So deviation of A square plus deviation of B square plus deviation of C square divided by the total number of points, which are 3. So this will give you variance, and variance will tell you how much the given data varies. For example, if variance of A is more, okay, okay, I think I have written the formula a bit wrong. Let me try to recorrect that. So we have to take only x points, right? So deviation of math of A square plus deviation of math of B square plus deviation of math of C square divided by 3. Similarly, comma deviation of physics of A square plus B square plus deviation of physics of C square divided by 3. So this is our deviation. Now, deviation tells you how much the data is varying, how much the data is varying, and the data which has more like a spread will have higher variance value. Okay, now the fourth step is that calculating covariance. After calculating variance, what we do is that we calculate covariance. Okay, so let me tell you the definition of covariance. We understood variance, right? Variance is nothing but like how spread the given data is, how spread the given one feature is, like how distinct it is. Now covariance, the definition of covariance is that, let's say I have one feature X and another feature Y, right? So covariance tells that how X is changing with respect to Y and how Y is changing with respect to X. So if X and Y are directly proportional, it means that if X is increasing, then Y is also increasing. If Y is increasing, then X is also increasing. Then we call that type of covariance as positive covariance, right? If in a given case, let's say if X is increasing, then Y is decreasing. In this case, we call this type of covariance as negative covariance. Now, if the given two features, x comma y does not have any sort of dependency on each other, then we call this as zero variance covariance, sorry, zero covariance, right? And why is it important? It tells you that how the given data is interlinked with one another. I can take an example as well, that in our previous example, if you see math marks, right? If a student is having high CGPA in math, then from the data we can tell that he is having high marks in physics as well. If he's having low marks in physics, then he's having like eventually having less marks in math as well. Now let's say I have another feature called as gaming, right? Gaming, uh, we can tell that if he's having high number of hours in gaming, then eventually he will have low CGPA in math and physics. It means that high gaming feature, then low math and physics feature. It means that the covariance is opposite, right? Then if it is opposite, then the we can tell that the covariance is negative. Now, how do we calculate that? We calculate covariance like this. So we have points, right? We have deviation points, which are this one, right? 8 minus 22 divided by 3. After that, 9 minus 22 divided by 3. Similarly, like I'm just writing math marks first, right? Math marks, 9 minus 22 divided by 3, and 5 minus 22 divided by 3. Similarly, if I write physics marks here, then 9 minus 22 divided by 3, 4 minus 22 divided by 3. Okay, let's not see this because this is a board error. So the covariance of math comma physics will be multiply this, and after multiplying, like multiply 8 minus 22 divided by 3 multiplied by 9 minus 22 divided by 3 plus 9 minus 22 divided by 3, 9 minus 22 divided by 3 plus 5 minus 22 divided by 3, 4 minus 22 divided by 3. After multiplying all this, how many points we have? First point, second point, third point. So divided by 3. This will be the covariance of the given data. Now, if the data, if math is increasing with respect to physics, let's say physics is increasing, then eventually because of physics, math is also increasing, then we get covariance as positive. If math marks is decreasing because of increase in the marks of physics, then we get covariance as negative, right? If there is no relation at all, then the covariance will be 0. Okay, so I hope you have understood. I hope you have understood, like how do we calculate covariance. Okay, now the thing we should understand here is that variance tells you the quality, or you can say the spread of one feature, right? Whereas covariance tells you how or how the data is moving with respect to another feature. For example, it tells you how the given two set of features are interlinked with one another. Okay, now what we do is that after calculating covariance, the fifth step is, let me remove all this. I don't wanna create a mess. So I'll remove all this stuff here. Okay, so the fifth step here is calculate eigenvectors and eigenvalues. Okay, so to calculate eigenvectors and eigenvalue, what is the equation? If you remember in math, we have a vector v here is the eigenvector, is equals to lambda I a, lambda I v, sorry, right? So if you take it here, you will know that A minus lambda I multiplied by V is equals to 0. So uh, from this we can extract that determinant of A minus lambda I is equals to 0. This is what we have understood from our last lecture. Now the thing you need to understand here is how do we get A? Right, if we know A, then we can extract eigenvalues and eigenvectors. So here we have something called as A is our covariance matrix. So what is covariance matrix? We create a matrix, let's say math, right? So we'll write math, we'll write physics. Similarly, math, physics. And whatever the covariance we have calculated here, variance of math, variance of math. When it comes to math and physics, we can put covariance of math, covariance of math, comma physics, covariance of math, comma physics. So this is it. So this is our A. We take A, and from A we'll get lambda, and lambda is nothing but our eigenvalues, and from lambda we can get the value of V, which is our eigenvectors. Okay, I'll show you how do we calculate in program, but after calculating it, we'll get let's say two eigenvalues, lambda 1 and lambda 2. So here the eigenvalue, the highest, let's say lambda 1 and lambda 2. Let's assume that lambda 2 is the highest one. So lambda 2 vector will be our PCA 1. So what I'm trying to tell here is that key, the eigenvalue, the highest eigenvalue will be the most important one. The highest eigenvalue will be our main PCA line. Why? Because it stores most of the information. After it, similarly, the second highest eigenvalue will be our second PCA line, and it stores the second important information. Like this, if we are having n PCA values, then you sort them in ascending order, and from this you can get PCA 1, PCA 2, PCA 3, like that. And after that, step 6, I believe. Step 6 is project the student's point onto PCA lines, right? And finally, whatever the data you get, whatever the graph you get, this graph will tell you the most important, tells you the patterns which are associated or involved in the n dimensions, or you can say n number of features. So this is the overall algorithm of PCA. First, calculate center. Number 2, recenter the given set of points to origin such that center will be origin. After that, calculate variance, calculate covariance, and from covariance create covariance matrix. And after getting covariance matrix, we know the value of A. Covariance matrix is A. From A, calculate eigenvalues and eigenvectors. And now here, the eigenvalue, the highest eigenvalue will be our PCA1, the second highest will be PCA2, the third highest will be PCA3. Like this, you will get n number of PCA lines. And remember that first PCA contains the most useful information, second PCA will contain the second most. Like this, you sort them and you draw the graph. When you draw the graph, whatever the graph you get, right, That will be the most valuable information you need to interpret patterns to get valuable insights from the data. So this is how we implement PCA. Now, let me quickly go to Jupyter and let me explain you the code as well. So I just wrote the code. I'll explain you. I'll give you a brief of what it is. So the step one is we are actually let me okay, I'll just explain you instead of writing. I wrote it few minutes ago. So here the first and foremost step is import all the necessary stuff. We are importing NumPy, matplot. Actually, let me code it, right? Okay. Okay, so in code, what we are doing is that we are first of all, we're importing all the necessary packages like matplot to draw graphs, NumPy because we are storing data in arrays, right? And after that, I'm importing a data set which is about images. So it stores the pixels in 64 dimensions. Okay, basically 64 features. Each image will have 64 features. Now, what I did is that I have implemented a function called as PCA from scratch. And here I am passing the given uh, data, and along with the data, I'm telling like how many components I need, how many PCA I need, PCA line 1, PCA line 2. 2 would be enough, 2 components would be enough. So I'm given n components is equals to 2. Now, what I'm doing here, I'm first of all calculating the center, and after calculating the center, I'm making the entire data come to the origin. So in line 2, I'm doing that. Now, after that, I'm calculating the covariance matrix. After calculating covariance matrix, I'm getting the eigenvalues and eigenvectors. Okay. Now, the thing I'm doing in fourth step is that this eigenvalues and eigenvectors are very random. Okay. So, the function which I'm using is lin alg.egih. So this is a function used from NumPy library. So this gives us eigenvalues and eigenvectors randomly, right? So to sort them in descending order, we are using this. So we are using like storing uh, sorted order, descendant sorted order of eigenvalues and eigenvectors. After calculating the eigenvalues and eigenvectors, I'm calculating the components PCA line 1, PCA line 2. Okay, now after that, I'm projecting the given points onto the PCA lines. And finally, I'm returning the projected points, eigenvalues, number of components, and mean. Okay, so this is what I'm doing in my function. Now, moving forward, I'm loading my data set. After loading data set, I'm taking PCA, like calling my PCA from scratch function. I'm storing the respective values like whatever it is returning me a two-dimensional space, right? So I'm storing the given space and the returned eigenvalues, components, and mean. After that, I'm showing how the space has rotated. Finally, I'm telling like how much the PCA1 is having, how much importance the PCA2 is having, and all. And finally, I'm showing that in a graph. So let me quickly run it. So the output should come. Let's wait for a few minutes. It is running. Okay, so you can see here I got the output. The space has rotated in such a way. Like the x-axis remained the same, but when I tilted PCA1 and PCA2. This is my new transformed space. After that, the PCA1 is having useful information about 14.9% and PCA2 is having 13.3%. Okay, and this is the graph. As you can see, the red points are similar points, sorry, and this points are similar, sky blue points are similar, like this you can tell. Okay, now this is the implementation. Okay, so this is the implementation of PCA without using any inbuilt libraries. Now let me tell you this as well, that there is a direct implementation of PCA from sklearn libraries. So this is the code, very easy code. That is why I don't want it to show you directly. Okay, so first we have implemented without using any libraries. Now this is the code with libraries. So first of all, we are importing all stuff, loading our data, and simply function. And when you do that, like here I'm giving how many components I want, how many PCA lines I want. I can give 3 as well, I can give 4 as well, any number of lines. After that, I'm drawing my graph. As simple as that. So I hope you have understood. You will find this code base in the GitHub repository directly. You can access it. I coded this thing, but the screenshot stopped in between, so I don't want to like reshoot it again. The students who are in the class, they have seen, but yeah. Yep. Okay, so I'll stop my screen share and yeah. So I hope you have understood. First of all, like we have discussed most of the concepts in linear algebra. Then we came to a concept called as eigenvectors and eigenvalues, and from that we have implemented a concept called as PCA. Right, PCA is the most important method used in machine learning. And then now we have seen how do we code it, how do we use it and all. So with that being said, if you have watched till here, then thank you so much for watching. It really means to me a lot. And in the next video, we are going to talk about SVD and going to build a recommendation system for Netflix, like a recommendation system that the platforms use, like Netflix and YouTube. They have recommendation systems, right? So we are going to build something similar using the concept of SVD. So with that being said, I will see you in the next one. Bye.